Hey friends, this is Professor Ross, and this video we're going to be talking about confidence intervals, one of our two main techniques we use in statistical inference, and a really powerful tool for us. So let's take a look at a few notes here. Uh, Share my screen. So statistical inference, confidence intervals. And we'll have a couple of key learning objectives that we'll be getting into when we're talking about confidence intervals. One is to be able to assess the role of variability, or also called error, when estimating a parameter. And the other is to distinguish between statistical significance and what we call practical significance. So let's dive in confidence intervals and talk about what they are. To set the stage, we'll talk a little bit about some practical ideas about why we even bother doing inference at all. And so you can check out this link here. It's an interview with a senator from a couple of years ago, and I just wanted to point out a key idea here that the senator didn't seem to understand really about the power of statistical inference. So the interviewer said, right now these numbers are showing about 53% of Republicans either want the corporate tax rate to be raised or stay the same. When selling this idea, do you see that as becoming a problem? So the she was trying to cite some statistics here, and Senator Zeldin didn't want to agree with the statistics. And he says, "What I have come in contact with would reflect different numbers." So it'd be interesting to see an accurate poll of 100 million Americans, but sometimes the polls get done on 1,000 people. So what Senator Zeldin didn't seem to understand was that what we can do with inference is take information from a relatively small group, say 1,000 people, and make inferences about a very large group, say all Americans. And we can do that with certain amount of confidence. And so when we talk about confidence intervals, we'll be able to talk about what we believe the interval of values is that a result might be like in the entire population, and how confident we feel that that value is in that interval. So let's get into the idea here. Confidence intervals help us answer research questions that we want to know about a parameter in a population. So we know what's going on in our sample. We have a statistic from our sample. How can we use that to figure out what's going on in the entire population? For example, what's the probability that something's happening out there in the population, or what proportion of the population has this or that, or for a population, what do we believe the mean is for this or that? So confidence interval is going to be super helpful for us as we're trying to find out what's going on in the population, and not necessarily when we have a hypothesis we want to test, but when we want to try to explore things and find out a little bit more about what that parameter is like in the population. A common example is elections, and as you know, whenever we're coming up to an election time, we tend to hear a lot of reports about predictions of who's winning a race, or what percent of people will vote for someone. So candidate A might be predicted to win 43% plus or minus 3% of the vote. And this here is a confidence interval. So it's an interval of values. If we go 43% plus 3%, that's as high as 46%, or 43% minus 3%, that's as low as 40%. And so we have an interval here, 40 to 46% of the vote is what is being said there. And that's a confidence interval. So it's a really common place that we'll run into confidence intervals. Another way, yeah, we might hear it said is candidate A is predicted to win between 40 and 46% of the vote. This is going to be the way that we tend to talk about it in the course, but I actually have heard it reported more frequently as something like this in the media. So, but they both mean the same thing. They're both talking about a confidence interval. They are separate, distinct from tests of hypotheses, but they are closely connected to test of hypotheses and the idea of statistical significance. And that's what we're going to dig into in the rest of this video, is finding that connection and really understanding what a confidence interval is and where it comes from. So we have an example to try this out. This is a really fascinating example. Can dogs sniff out cancer? So dogs obviously can smell a lot of things and smell things typically better than humans can. But some people have put time and effort into trying to research whether dogs can smell if a person has cancer. This could be a really powerful medical diagnostic in that it's not invasive, it's not especially challenging, except you need to put some training into training dogs to do this. Let's talk a little bit more about this specific one. Sonoda et al. In 2011 reported that Marine, a black lab, made 33 attempts to identify one cancer patient out of 5 people. So they put 5 people in front of Marine, and they said, Marine, uh, find the one that has cancer. They had trained Marine to sniff it out. By chance alone, Marine should have a 20% chance of getting it right if Marine's just guessing. She correctly identified 30 cancer patients in her 33 attempts. She had a 90% success rate. Way, way, way different than just guessing, right? 20% success. The null distribution looks something like this. We'd expect to see in 33 tries Marine to get somewhere between, 12 to 30% correct if she's just guessing. She got 90% correct. Totally different. This is where a confidence interval can be helpful, because we clearly reject a claim like she's just guessing. It's clearly not 20%. But then the question is, what percent can she identify? Right? We'd like to have a sense of how well Marine can identify cancer. It's clearly not 20%. What is it? So here's a technique we can use to help us get a sense of this. The answer is going to be a confidence interval. And here's one way to develop and find that confidence interval. We can say, okay, pi as 20%, we reject that. Let's try some other pies, maybe 30%. Maybe that would go along with our results better, or maybe 40% or 50% or 60 or 70, especially when we get up to 80 and 90%, that should go along pretty well with our results. We can run a hypothesis test over and over and over again, find the p-values, and if it's a low p-value, we reject that pi that we've tried. If it's a higher p-value, higher than alpha is 0.05, then we'd say, okay, we're not rejecting it. It looks like it would be a plausible value for our parameter. And so we kind of go through and just try a whole lot of p-values and see if we can find some kind of plausible range of values for the parameter that seem to go along better with our result that Marine actually had. That range of plausible values is called a confidence interval. So it's the interval of plausible values for pi that would not be rejected for a two-sided significance test with a 0.05 level, and we call that the 95% confidence interval. You'll notice if the significance level is 5%, we call the confidence interval a 95% confidence interval. Those always add up to 100%. Also, a quick note, we said we would use a two-sided significance test. If you use a one-sided significance test, that actually changes the p-values, right? Remember that. And so that gives us a one-sided confidence interval. It's a little bit different. We won't deal with those in the course. So we'll always be thinking about a two-sided significance test. We can say we are 95% confident that pi, the true value out there in the population, is in that interval. For example, for Marine, what percent can she actually sniff out cancer? We'd say we feel 95% confident that the rate she can actually identify cancer is somewhere between these two values that we find. Another way to say it is if we sampled the process over and over, 95% of the time, the confidence intervals would have our parameter inside of them. So we feel this confident that we're actually capturing the parameter inside our interval. We can technically calculate a confidence interval for any percent we want. So I said 95. We could do this with 96 or 82 or 15 or anything between 0 and 100. Um, the most common are 90, 95, and 99. And the way we can get the different ones is just by changing the alpha level for the cutoff that we're looking at. So if we change it to 10%, then that's a 90% confidence interval. If we change our alpha level to 1%, then we're looking at a 99% confidence interval. So that's how that works. Let's try this out. So what I'm going to do is I'll come back to this slide here in a little bit. Let's take a look at this here. I've created a little table where we can record some results from looking at possible parameter values for marine, and we'll check the p-value, and then we'll decide, should we reject that as a possible p-value or as a possible parameter, excuse me, or is it plausible? So let's try it out. Let's say we thought, okay, clearly marine's not a 20% success rate. Maybe she's 70% success rate. Let's go ahead and bring up our applet here. And let's say we thought marine's probability of success was 70%. She had 33 tries. And let's run our simulation 10,000 times. It'll run that pretty fast for us. Now, this is what we'd expect to see if she was a 70% sniffer. Results somewhere between probably, 18 to 27, 28 would be fairly common. What did Marine do? She did 30. She got 30 correct. And then let's make sure we do this as a two-tailed test so that it lines up appropriately with the confidence interval we're talking about. So here's the p-value for the claim that she's a 70% sniffer. Well, her result was way out here, and the other tail is also really small. There's only a 0.0068 so p-value, so that means less than 1%. We're talking about very strong evidence against that claim that she's a 70% sniffer. So we got a what was it again? 0.0068. I think it's going to round here for me. Yeah, 0.01. And if I'm using, let's stick with that alpha of 0.05%, I'm below that. So I would reject. She is not a 70% sniffer. Is she a 71% sniffer? Is she right 71% of the time? Let's go ahead and change this to 71. Redo my simulation. I still got 30 in there and two-sided. Now my p-value has edged up a little bit. You can see that I got a little bit more going on there, but not a whole lot, 0.0121. So 0.0121. Is it plausible that Marine is going to get it right 71% of the time when she's sniffing out cancer? Well, really low p-value, reject that claim. She's not a 71%. Let's try 72. So you might start getting familiar with how this pattern goes. We can change this to 72. We can check the p-value. Might see that, hey, it's gone up a little more again. Still not a lot, but 0.0172 is going to round to about 0.02. I'm still below alpha of 0.05, so I'm going to reject. Now, I'm not going to sit here and go through every single one of these cells in the video. I encourage you to pause the video and try this out yourself a few times on the applet and see if you can start seeing a trend in the p-values that are coming out. What I have done is, I have filled in the whole table for us here and done a little bit of coloring for us to get a sense of what's going on. So you can see here, here's the 0.01, 0.01 p-value, 0.02 p-value, 0.02, 0.03, 0.04, 0.04. Can you see the trend? They're going up a little bit each time. Why are these all colored red, and why do I have R's here? These are all p-values that are below 0.05, and so we would reject these claims. If someone tried to claim, you know what, Marine is a 76% cancer sniffing dog, with the evidence that we have from our sample, we should reject that claim. It looks like she's better than 76%. On the other hand, if someone claimed that she was a 77% cancer sniffing dog, if we check that against our statistic, we find a p-value of 0.06, a little bit above the 0.05 cutoff. 77% is closer to that result we saw that was around 90%. It seems like it might be plausible. Maybe Maureen had a really good day. The day we saw her, she got 90% right, but typically she's, in the long run, she's around 77%. That's plausible. These p-values just keep going up. 9, 13, 13, 19, 25. They just keep going up higher and higher until we are right around the value we actually saw. And then they start dropping down again after that. All of these values in here, could Maureen be a 78% sniffer? Yeah, plausible. 79%, plausible. 80%, plausible. All the way up to around 90%, very plausible. That's just what we saw her do. Could she really be as high as a 95%? Yeah, that goes along with the data we saw. It would be plausible. We would not reject that claim. Could she be a 97% cancer sniffer? That would be plausible based on the evidence we saw and our test that would give us a p-value above 0.05. Could she be a 98% cancer sniffer? Now that we've gone too far, right? 98% is too high. We get a p-value that drops below our alpha cutoff, and we would reject a claim of 98%. And similarly for 99. What do we have? We have an interval of values in green here that are all plausible values for what Maureen might actually be able to do out there in the long run. Could she actually get it right 77% of the time? Yes. Up to 97% of the time? Yes. That's what we call the 95% confidence interval. It is from 77 to 97%. And we feel like in the long run, Maureen's true percent of correctly sniffing out cancer should fall somewhere between 77 and 97%. Now we got to connect that to our key learning objective, that there's some variability here. We're trying to estimate the parameter, the true percent Maureen will get right, and we can't pin it down exactly. There's a little bit of variability. We know it, we feel quite confident, 95% confident, that it's going to fall somewhere in that interval. Let's talk a little bit about the other interval sizes. So let's say I wanted to be more confident. So I'm 95% confident. There's a 5% chance I could be wrong. What if I changed and I wanted to be even more confident, 99% confident? I want to be really sure I was pinning down Maureen's true percent. Well, what would happen? Instead of my cutoff being at 0.05, it's going to be down here at 0.01. Now, this one got rounded up a little bit. That one would have been just below 0.01. The rest of these would all be above 0.01. So I'd be looking at these guys also being in my confidence interval. Same thing up here. This one here is going to end up falling in my confidence interval as well. So what has happened? My confidence interval went from being narrower to being a little bit wider. My 95% confidence interval, I'll abbreviate it as CI a lot, went from 0.77 to 0.97. But you can see my 99% CI is a little bit lower, 71% to a little bit higher, 98%. There's a trade-off here. I'm more confident, but my interval is wider. I haven't quite honed in quite as tightly on what marine can do. Can you guess what the trade-off will be the other direction if I lower my confidence? Let's say I only want to be 90% confident. I'm okay with being wrong 10% of the time. Let's look at what happens. Our cutoff now changes to here. I'm just going to hit these all in red. And this one changes to here. And I end up with a narrower confidence interval. My 90% is narrower, 79 to 96. I can hone in a little closer and say, hey, you know what? I think marine's going to be somewhere in this narrower interval, but the trade-off is I'm wrong 10% of the time instead of 5% of the time. So the main idea there is that there's a trade-off. Higher confidence has to go with a wider interval because we can see those p-values widen things out. All right, so that's the idea of confidence intervals and how we can use them to understand where a parameter might be and how the variability fits in there.